Hi, let's start with concept capsules. The topic that we're going to look at today is hypothesis testing. So you'll see hypothesis testing is part of your CFA level 1 quants curriculum, CFA level 2 quants curriculum, as well as the FRM curriculum. Now this is a topic that is quite dreaded by students, especially for CFA level 1. So let's see what we can do to make this slightly easier. Now first, let's understand what hypothesis testing is all about. Hypothesis is, think of it as an opinion that you have here, right? Any claim that you're trying to make. But this claim is not substantiated yet. It's just a statement that you have made. You have not tested it out yet. So for instance, take this as an example. The mean lifetime of men is less than that of women. So that is a claim that you're making. That is a statement that you're making, but you don't have evidence for it yet. So you need to prove it. And that's where hypothesis testing comes into the picture. So hypothesis is an assumptive statement about a problem, idea, or some other characteristic of a population. Now, in order to test the hypothesis, you need to collect some data. So testing would involve collection and examination of a representative sample. So of course, we can't go out and study the entire population because it's going to be too time consuming, it's going to be too expensive, and we might not even be able to count the entire population. So the only resort that we really have is that we study a sample, we draw a sample from that population, and we come to a conclusion about the entire population using that sample. So that is what hypothesis testing really is all about. Okay. Now let's look at the main thing. That is the steps in hypothesis testing. Now these steps are the backbone of what we are trying to do here. Now, a lot of people would find hypothesis testing tough because of the number of formulas that are involved, because they're not really fluent with what null and alternative hypothesis is. They don't really know when to reject or fail to reject a hypothesis. What we need to do is we need to follow these 6 steps in exactly this sequence. What you realize is that hypothesis testing is actually quite a mechanical process. Regardless of what you're testing, regardless of which distribution we are talking about, these 6 steps are not going to change. So whichever hypothesis testing question you have, you simply go ahead and implement these 6 steps in exactly the same sequence and you'll have your answer. Now keep in mind that we're not saying that you won't have to memorize any formula. You will have to memorize some formulas here because there are multiple distributions at work. We also need to see that which distribution would be required for the particular question that has been given. So what are we actually testing? Are we testing the mean? Are we testing the variance? Are we testing mean difference, difference of mean, or equality of variances? There's so many different tests that could be there. So depending on what you're trying to test, your statistic, the test statistic is going to change. Your distribution is going to change. So yes, there are quite a few formulas that would be involved there. So we will have a t distribution, we'll have z distribution, chi-square. In your level 2 curriculum, you'll have Durbin-Watson tests as well. So there are many different kind of tests that you'll be running. But remember, these 6 steps will always be implemented in exactly this sequence. So if you understand the steps well, you'll be able to solve any question. So remembering the formulas is not going to be sufficient. So even if you remember the formulas and if you're not able to implement it as part of these 6 steps, you'll still not be able to come to the conclusion. And that's what actually happens with most students. They would focus so much on memorizing those formulas that they forget that these are the 6 steps that need to be followed to get to the conclusion. So just being able to calculate the test statistic by remembering the formula is not going to get you the marks here. So you need to make sure you understand the process well. And in your own interest, try practicing all the questions that you're doing in hypothesis testing in exactly this sequence only. It's going to help you. Right now, after looking at the steps, we'll do a couple of examples as well to see how these steps do not change regardless of whatever question you have. So whichever question you have, simply implement these 6 steps in the sequence and you'll have your answer. So let's look at the sequence. The first one is statement of both the null and the alternative hypothesis. Now this is a step that is extremely important because if you get the first step wrong, your entire question is going to be wrong. And this step is actually not that tough. A lot of people do get confused with null and alternative hypothesis. There are some basic rules to remember while creating null and alternative hypothesis, and you'll be good to go with this. So we're not going to cover this step in a lot of detail because remember, the focus of what we are trying to do in this concept capsule is to make sure that we understand this particular sequence that we have to follow. So we're not going to cover any step in a lot of detail. Focus is on the big picture here, that what are the steps. However, we do have a separate video on null and alternative hypothesis. We do have a separate concept capsule for that. So in case you're getting confused in this first step, make sure you watch that first and then you come to the steps. All right. Now, first is statement of both the null and alternative hypothesis. One quick way to remember what goes into the null hypothesis and what goes into the alternative hypothesis is that, remember, in null hypothesis, you will have an equal to sign. That equal to would include equal to, more than equal to, or less than equal to, right? So one of these three has to go into the null hypothesis. The other part of the distribution is going to go into the alternative hypothesis. Typically, we take that statement that we are trying to test as the alternative hypothesis, so that if we reject the null hypothesis, then it's the alternative hypothesis that we're going in favor of. That's the first step. This is going to remain the same everywhere. Second one, identify the appropriate test statistic and its probability distribution. This is where the difference comes in when you test one thing or versus something else. So let's say if you're testing mean, then you will be using either the t distribution or the z distribution. If you're testing variance, then you'll be using the chi-square distribution and so on. So the step remains the same, but the distribution that you're using and which test statistic is appropriate, that part changes. So this is where you'll have to be careful. Third is you specify the level of significance. Now, this is not really a problem. Typically, you will be given this as part of the question. The most common level of significance that we use is 5%. So you could be given 5%, 1%, or 10%. So whatever is given in the question, you simply go ahead and use that. So this is something that is not really a problem. Now, the fourth one is state the decision rule to guide you in choosing whether to reject or to not reject the null hypothesis. So in this step, we clearly mention that under which condition will we be able to reject the null hypothesis and under which condition we will fail to reject, what we call as FTR, fail to reject the null hypothesis. Another term that is used is DNR, do not reject the null hypothesis. So you can use these abbreviations as well. After this step, what we will be doing is we will be calculating the sample statistic. Again, the calculation of sample statistic will depend upon what we are trying to test. So you will have different formulas here. So just like in step 2, here as well, you'll have to know that which formula is useful. So you will have to memorize those formulas and you'll have to implement it at this particular step. Finally, once we have conducted this test, we come to the main part. That is what we were running the hypothesis test for in the first place. And that is that we make a decision based on the sample results. So that is going to be the final step. So make a mental note of these 6 steps. This is what we are going to implement in the next 2 examples. Now let's have a look here. First, let's try to test a single mean. Now you've collected data on the annual rainfall, which is in centimeters, in a certain country over the last 10 years. So we'll keep marking whatever is useful in the question so that we are able to use that when we solve it. So over the last 10 years, so how many years of data are we using? It's 10. So 10 is essentially the n. And we have determined that the average rate of rainfall is 26.6 centimeter. So that is the average rainfall that we have recorded. That is 26.6. That is the other data point. The standard deviation is 1.43. So we need to use these two. Now, financial analysts wish to determine whether the average rate of rainfall has increased from its former value of 23. Now pay attention to this term, increased. They're specifically asking you that has the rainfall increased from the value of 23, which means they're not looking at the decrease part at all. They're only looking at the increase part. Now that tells you that this is a one-tailed test because we are not looking at both the sides of the distribution. We are specifically interested in one side, and that is an increase. So it is a one-tailed test. and the comparison value is 23. Now you need to carry out a statistical test at the 5% significance level. Assume that the annual rainfall quantities are normally distributed and recorded independently. Now in this case, we will end up using the t distribution. Why? Because we don't know the variance. So let's try solving this. We follow the exact same 6 steps. Now the first one is that we have to formulate the hypothesis. So we have to pay a lot of attention here, because if we get the first step wrong, then the entire question and our conclusion is going to be wrong. Now we're specifically testing whether the mean has increased from 23. So that is something that goes into our alternative hypothesis. The alternative hypothesis is mu is more than 23. So remember, it becomes a one-tailed test. Now, if alternative is that mu is more than 23, what are the remaining possibilities that need to go into the null hypothesis? That is, mu is less than or equal to 23. Because remember, the rules of the hypothesis is you need to have an equal to sign somewhere in the null hypothesis, and that both null and alternative hypothesis should be mutually exclusive and collectively exhaustive. So there should be no other value possible apart from these two, and there should be no overlap between the two hypotheses. So all those 3 conditions are actually being fulfilled here. So that's where the step is taken care of. Now let's move on to the next step. We need to identify the appropriate test statistic. Since we are testing a single mean and we don't know what the population variance is, we will go in for a t-test. Now this part, that which test are we going in for and which test statistic do we have to use, that is something that is going to change depending on the test that we are trying to conduct. So in this case, it is the t-test, and that's our t-statistic, that's the formula, but that's not going to remain the same all the time. So if we are testing for the variance, then we're not going to use this. We are going to use the chi-square distribution instead. Now specify the significance level. That is 5%, something that has been given to us in the question itself. Now 5%, if you look at the t-value, the critical value in the table comes to 1.83. So till now, we have not even applied the formula for the t-statistic, so keep that in mind. We can get the critical value by just looking at the t-distribution table for 5% level of significance. After this, we have to state the decision rule, which means that we have to specify when are we going to reject or when we fail to reject the null hypothesis. Now, the alternative hypothesis is that mu is more than 23. Null hypothesis is that mu is less than or equal to 23. Now, in order to conduct the test, we will compare the value to not 23 but to 1.83. So keep that in mind. We are not using 23 right now. We will use it later. Right now, our benchmark will be 1.83. So that is what we are going to compare our t-statistic with. So the decision rule will be that if our t-statistic, if our test statistic is more than 1.83, why are we saying more? Because this is a one-tailed test where we are specifically looking at is mu more than 23. Hence, if our test statistic is more than 1.83, that's when we are going to reject the null hypothesis, because null hypothesis said that it should be less than or equal to. So after this, we calculate the test statistic. This is the formula that we have to apply. So x bar minus mu divided by s by root n. X bar, if you see the question, that was 26.6, mu was 23. These were the figures. We have to look at both the population as well as the sample. In the denominator, you have, s by root n. S, we have seen, that is given to us as 1.43. So we put that number here. The number of years is 10. So root of n becomes root of 10 and we get 7.96. So of course, as we just said, your test statistic is going to depend upon which test you are trying to run. Now, what are we going to compare this with? We will compare this to the critical value that we had earlier. So 7.96 is now getting compared with 1.83. Remember the decision rule. We said we reject the null if the test statistic is more than 1.83. In this case, it comes to 7.96, which is clearly more than 1.83. So it's lying outside of that region. So when the value is lying outside of that region, we can easily reject the null hypothesis. So in this case, our decision is that we go ahead and reject the null hypothesis, and we say that we have sufficient evidence to reject the null hypothesis because 7.96, our test statistic, is much higher than the critical value at 5%, that is 1.83. So it's reasonable to conclude that the average annual rainfall has increased from its long-term average of 23. So we have enough evidence to show that, so we can safely reject the null hypothesis. Had this value been lesser than 1.83 or equal, then that is something that we would not have been able to reject. Now let's try out another example and see if the steps can be applied there as well. Now we'll test a single population variance. Now for the 15-year period between 1995 and 2010, ABC's monthly return had a standard deviation of 5%. So that is the standard deviation that we have been given. Now Matthew wishes to establish whether the standard deviation witnessed during that period still adequately describes the long-term standard deviation of the company's return. So 5% is the value that we are looking at for the long term. Now to do this, to test this, he collects the data. So remember, for testing any hypothesis, you need to collect the data. So that's what Matthew is doing here. He collects the data on the monthly returns recorded between 1st Jan 2015 and 31st December 2016, which is a period of 24 months. So our N is 24. And then he computes a monthly standard deviation of 4%. Now we need to carry out a 5% test. So that is the level of significance that we are testing at, to determine if the standard deviation computed in the latter period is different from the 15-year value. So we need to compare these two values, but remember, the test that we are going to conduct is for variance, not standard deviation. So we're not going to use 5% and 4%. We are going to use the squares of these numbers because variance is the square of standard deviation. Now, in this case, can we still use the t distribution or the z distribution? Now think about it. When we talk about variances, variances are squares of standard deviation. That means that you cannot have a negative number. If we talk about t distribution or z, then it's something that goes from minus infinity to plus infinity. But in this case, that is not going to work because we need to have a distribution which is bound by 0 on one side. So it cannot go into the negative. So in this case, the distribution that we will rely upon is the chi-square distribution because it is bound by 0 on one side. Now just a quick recap of the numbers that we are going to use. 5% is what we're testing against. 4% is what the standard deviation, what our sample has given to us. So we'll square both of these numbers. So 4% square and 5% square. 5% is the level of significance that we are looking at. And the n is equal to 24. So now let's implement all the 6 steps again. Now step number 1 is formulate the hypothesis. What are we comparing? We want to see if the variance has actually changed from 5%. So our null hypothesis, remember it needs to have the equal to sign, is that your variance is equal to 0.0025. Remember, in the question we have been given the standard deviation and not the variance. So we have to square 5%, which comes to this, and we will square 4%, which will come to 0.0016. So our null hypothesis is that your variance is equal to 0.0025 versus what will be the alternative hypothesis? If we have equality in the null, then you should have inequality in the alternative. That means your variance is not equal to 0.0025. That means it could be more or it could be less than this value. That should tell you that we are dealing with a two-tailed test because we are looking at a higher as well as the lower side. So we are looking at both the tails of the distribution. So it's a two-tailed test that we are going to run. Second is that we identify the appropriate test statistic. So in this case, what we're just discussing, that we will go in for the chi-square distribution because we need a distribution which cannot go into the negative here. So chi-square distribution does not have a negative value and it is bound by 0. What is the test statistic formula we are going to use? So chi-square at n minus 1. So n, remember, was 24. So n minus 1 into s square, which is basically the sample standard deviation that we had, divided by the population variance. So sample standard deviation square would give you the sample variance. So that was the second step. Now the third one is that you specify the significance level. That is something which has already been given to us in the question, and that is 5%. So we go to the chi-square table, we look at 5% value, and the values that we get, the critical values that we get, are 11.689 and 38.076. Now 11.689 and 38.076 essentially means that if our value lies between these two numbers of 11.6 and 38.07, then we will fail to reject the null hypothesis. We won't have sufficient evidence to reject the null hypothesis. But if the value lies outside of this range, that means that if it is lesser than 11.689 or it is more than 38.076, then we can safely reject the null. So that becomes our decision rule. So you reject the null if test statistic is less than 11.6 or it's more than 38.07. And if it lies within this boundary, then we fail to reject. So the next step will be to actually calculate the test statistic and see in which region does that value lie. So when we calculate this, we put in all the numbers given in the question in this formula. N was 24. Your sample standard deviation was 4%, so we square that. Your population standard deviation was 5%, so we square that in the denominator, and that gives us a value of 14.72. Now 14.72, as you can see, lies between these two values. So it does not lie outside of the range, it is within this range only. That basically means that we cannot reject the null hypothesis. So we say that DNR, do not reject the null hypothesis, so we don't have sufficient evidence to reject this null hypothesis. That is what our conclusion is. So this test statistic lies between the two. So we have insufficient evidence to reject H0. What is the economic decision here? So it's reasonable to conclude that the latter standard deviation value is close enough to the 15-year value. So it's both the values are quite close to each other. That is what our conclusion is essentially. So as you saw, the steps that we followed were exactly the same in the two, even though the tests that we were running were completely different. But our steps did not change. How we calculate the test statistic and which distribution we use, those are the only two things that are changing. But everything else has remained the same. So you can use this to understand how hypothesis testing works. And wherever you're applying hypothesis testing, you can straight away start working through all these steps to get your answer. So I hope this helps you in understanding hypothesis testing better.